This selection of different-looking grains were once all similar marine aragonite ooids, but they were raised above sea level and rained on, under different climates, for 1 to hundreds of thousands of years. This video documents the petrographic changes these ooids have undergone, using just 1 or 2 samples from 7 different freshwater systems across Europe and the Caribbean. The first sample is an ooid grainstone from an excavation into a supratidal flat that occurs on the west side of Little Ambergris Key. It was collected about 150 centimetres beneath a black microbial mat that covers the supratidal flat, and about 150 centimetres above the water table. Curali, Weaver and Sala, 2008. Most of the samples used in this video were fragile when collected. To preserve the original fabric, they were impregnated with epoxy before the rigours of thin section preparation, and the epoxy was dyed blue to highlight the distribution of pores. The first thin section shows only ooids arrived at the ambergris depositional site, where they were partially cemented by transparent calcite cement. The cement's crystals occur predominantly between closely spaced ooids, but the small gaps between ooids by the brown asterisks are cement-free. The shape of the cement crystal surfaces facing intergranular pores vary. Some are concave by the red asterisks, some are euhedral by the purple asterisk, and one ooid has cement with a convex surface by the green asterisk. Under cross-polars, the ooid's aragonite has a light brown birefringence colour, and the calcite has anomalously bright second-order birefringence colours due to this thin section being only 12 microns thick. This image is from a different area of the same ambergris thin section. Concave final surfaces occur by the red asterisks, and rhombic terminations occur by the purple asterisks. The growth of the rhombic crystals in the boxed area is enlarged and described on the next slide. The image is rotated 90 degrees and now fades to a cathodoluminescence image. The epoxy resin is light grey and occurs in intergranular pores between calcite cement crystals and intragranular pores within the ooids, including 10 micron sized endolithic borings and faint lines of nanopores in the ooid cortices. These ooid intragranular pores were created in the marine realm and remained practically unchanged while at the ambergris site. The calcite cement crystals are grey. 2 central crystals show early faint internal growth zones. The growth of these calcite cement crystals is now discussed using a simplified sketch. The 2 calcite crystals that nucleated on ooid 1's surface left faint internal rhombic zones during their early growth, but later, and all other crystals, are unzoned. As the crystals grew against one another, intercrystalline boundaries formed, but some crystals, for example crystal 2, project into pore space and are terminated by euhedral surfaces. These rhombic surfaces have a similar shape to the growth zones in the early part of crystal 1, suggesting all crystals had the same rhombic growth surfaces throughout their growth. James and Jones, 2015, figure 25.5, show a thin section image with arrows pointing from intergranular calcite cement to ooid cortices, and a caption reading, "Caught in the act." The dissolved carbonate has been precipitated as intergranular cement. Unfortunately, the arrows point in the wrong direction, and they imply dissolution and precipitation were coeval, with a transportation distance of a millimetre or so. The ambergris sample, however, shows the source of carbonate for its intergranular cement was not within the area of the thin section, and although aragonite dissolution may have been the source of carbonate, it provides no evidence from where this was obtained. The next two samples come from South Julter's Key, north of Andros Island on the Great Bahama Bank. The two samples were taken from a core, one sample from the vadose zone, 30 centimetres below the core's top, and one sample from the phreatic zone, 3.6 metres below the core's top. Halley and Harris, 1979. Contemporary vadose cement on South Julter's Key occurs in thin lenses of fresh water above the water table, which is tied to current sea level. Harris, 2025. The Key's surface is up to 6 metres above sea level, and the ooids have potentially been exposed to rainwater for about 1,000 years. Chung and Swart, 1990. The Julter's vadose thin section, like the ambergris vadose section, has calcite cement partly filling its intergranular pores. But, unlike the ambergris section, many of its ooid cortices have undergone extensive dissolution. The cortices in many ooids are composed of sheet pores about 10 microns wide, alternating with similarly sized, partially dissolved aragonite layers. The intergranular calcite cement in the boxed area is looked at next. Several ooid pairs, including ooids 1 and 2 and ooids 3 and 4, are joined by cement with concave final surfaces. However, ooids 2 and 3 have other cement crystals on their rims that have convex final surfaces facing open pores by the red asterisks. The concave surfaces were interpreted by Dunham in 1971 to record the position of the air-water meniscus interface in many vadose sediments. Convex surfaces have been interpreted as pendant cement that cast the air-water interface of water drops hanging gravitationally from the underside of grains. The large convex crystal on ooid 3 would fit such an interpretation, but many small convex crystals occur on the ooid rims that are randomly oriented by the red arrows. Internal growth surfaces within calcite crystals can be revealed by cathodoluminescence. Such information could be used to reconstruct the growth of Julter's intergranular crystals. But unfortunately, the Julter's intergranular calcite Luminesce is dark grey, with only irregular patches of lighter grey material, and a rhombic-shaped growth next to the red asterisk. What CL does clearly show is the distribution of sheet pores and endolithic borings in some of the ooid cortices, as they are filled with epoxy that luminesces white against the dark grey aragonite. The Julter's phreatic thin section shows a large central ooid whose unstructured outer cortex has been largely dissolved. Most other ooids have a similar dissolution pattern to that described for the vadose ooids. The intergranular calcite cement in this phreatic section has crystals that nucleated on the ooid surfaces and grew to partly fill most intergranular pores. Unlike the vadose crystals, they are all terminated by rhombic euhedral growth surfaces. The Julter's vadose and phreatic sections have both cemented intergranular pores and dissolved ooids. Either these two processes did not occur at the same time, or if they did, the fluids in the two reaction sites did not mix. The next sample comes from wind-blown coastal dunes that were piled up against a vertical cliff of Miocene reef limestone at Centre de Tombe, southeast Majorca, described by Clemenson and others. This Pleistocene aeolianite is composed mainly of skeletal carbonate grains that are like those forming today on a shallow marine platform off Majorca. According to Fornas and others, this aeolianite was deposited during glacial intervals when sea level was low and strong westerly winds blew across Majorca. The sample from the vadose zone in the middle of the outcrop, meters above sea level, was thin-sectioned and is shown on the next slide. This image shows a variety of grains, including superficial ooids and ooids with multiply layered cortices. The grains are held in place by a fringe of transparent calcite cement crystals and some larger cement crystals that are seeded on single crystal grains. The boxed ooid 5 on the right is enlarged next. The position of ooid 5's rim is preserved by an outer ring of cortex aragonite and by calcite cement that encrusts the ooid's surface. Ooid 5's inner cortex consists of aragonite layers alternating with sheet pores that have, together with ooid 5's nucleus, collapsed to the floor of the youngest pore. The intergranular cement has a different fabric to that shown in previous thin sections. It nucleated on ooid surfaces at points about a micron apart and grew to form a druzy fabric before terminating. After only about 10 microns growth into the 100 micron sized intergranular pores. The notion that the dissolution of the ooid cortices was caused by the infiltration of undersaturated intergranular water does not fit with what you can see here. This water's potential for dissolution would be greatest on entering the ooid, and as it moved deeper into the cortex, would decrease as its saturation increased, and its aggression would fade away. However, here it can be seen that the ooid's rim is composed of aragonite, and the inner cortex is evenly, though episodically, dissolved across the whole width of the cortex. And across polars, the position of the cortex's collapsed aragonite layers is emphasized by the distribution of its intervening black pores. A second Pleistocene aeolianite is examined from the top of. This Spanish sample shows ooids 6, 7, and 8 have lost at least half their cortices. The intergranular pores are sometimes filled completely with calcite cement. The few that are incompletely filled are lined by crystals with euhedral surfaces, by the red asterisk. The cement in pores by the purple asterisks has been dissolved. These new pores with black margins cut irregularly across and hence are later than the cement. The restriction of this late dissolution to certain pores implies only they were in fluid connection. Ooids 6 and 9 are examined next at a higher magnification. The rim of ooid 6 is partly preserved, on the left, by a slither of aragonite cortex, the rest of its rim by intergranular calcite cement. The 5 or so cortex aragonite layers, separated by sheet pores, and ooid 6's nucleus, have fallen away from the top of ooid 6's rim, causing the youngest pore to become crescent-shaped. This cortex pore is the first described so far to contain intergranular calcite cement. Ooid 9 has a more significant amount of calcite cement present in its outer cortex pore, on the lower right. The sequence that created ooid 9's lower rim is, first, the intergranular cement nucleated on the ooid's rim while it was still composed of aragonite, and grew into the intergranular pore away from the ooid's surface, shown by the purple arrows. Second, 2 pores, several microns wide, were dissolved in the cortex. The youngest pore, too, exposed the base of the intergranular cement crystals. Third, calcite cement seeded on the base of these intergranular crystals and grew towards the ooid's center, shown by the green arrows. The number of diagenetic events to affect the Spanish sample has increased over those affecting the ambergris or Jultus samples, and it is the first to show its enlarged cortex pores received intragranular calcite cement. Sample 5 is a Pleistocene oolite that comes from the 200,000-year-old Corinth Peninsula, that was constructed from a few faulted, shallow marine glacial-eustatic terraces, described by Collier and Thompson in 1991. The sample is from a road cutting near Eximilia. Cross-bedding is prominently displayed at this outcrop, where well-cemented lamina weather out, alternating with poorly cemented lamina that weather in. The outcrop is capped by a calcite, indicating subaerial exposure and soil formation. The Eximilia lamina on these scan-thin sections are between 3 and 5 millimeters thick. The left stained image shows red-stained lamina composed of calcite, alternating with mauve lamina composed of red-stained calcite and blue-dyed epoxy-filled pores. On the right, the higher magnification and unstained image shows two blue lamina dominated by blue epoxy-filled oomoles that alternate with lamina composed of both calcite ooids and calcite-filled intergranular pores. The margin of most lamina are diffuse and irregular, emphasizing the diagenetic origin of these lamina. The areas number 1 and 2 on the right unstained image are enlarged on the next slide. On the left, Area 1 ooids have cortices composed of a mosaic of calcite crystals. Some show concentric lines inherited from the cortex's original fabric. The intergranular pores are filled by a mosaic of calcite cement crystals. But this cement in some pores, by the red asterisks, has been dissolved. New pores with black margins cut across the previous cement, much like that described in the Spanish aeolianite. On the right, Area 2 ooids have had their cortices completely dissolved to form oomoles. Their intergranular pores are filled with calcite cement. A few incompletely filled pores, by the red asterisks, are lined by cement crystals with preserved euhedral surfaces. The late dissolution that affected the intergranular cement in Area 1 did not affect that in Area 2. Corinth ooids, not from the Eximilia road cut, were described by Richter in 1983 to have aragonite cortices. All the components of the Eximilia sample are now diagenetic. Although some original fabric of these lamina can still be detected, all the components are secondary. The reason why Area 1 is now so different from Area 2 is obscure. Presumably, some depositional features control their diagenesis, as crossbedding is now obvious at outcrop. The next samples are from the Miami oolite that was deposited about 120,000 years ago, during the last interglacial high stand of sea level, according to Harris and Perkis, 2019. Two samples of this oolite are figured in this video. I collected them in 1985 from the subaerial banks of the Coral Gables waterway. Halley and Evans, 1983. The preservation of ooids in the first thin section is highly variable. Some still retain aragonite layers that alternate with concentric sheet pores. Some have their cortices replaced by mosaics of irregular-shaped calcite crystals, and some are oomoles containing no aragonite but concentric shells of brown material. Patches of oolite have their intergranular pores filled with calcite cement. Other patches have none. The calcite crystals at the contact between these patches have irregular margins caused by dissolution. This thin section has similar individual features to the Corinth section, but they are randomly distributed, not organized into layers as occurs in the Corinth sample. Ooid 10, upper left, at the margin of a cemented patch, is described next. The outer margin of ooid 10 is patchily preserved. On the right, its rim is preserved as a curved line by 10 micron sized intergranular calcite cement crystals. On the top left, its rim is not preserved. It is assumed it was also cast by the intergranular calcite crystals that subsequently have been dissolved. Under crossed polars, the intergranular cement in the lower left corner of this image, with a pink and green birefringence colour, extends into the cortex pore by the red asterisk. This calcite nucleated on the base of the intergranular cement crystals and grew into cortex space once it had become a fluid-filled pore. ooid 10's left margin in the box is now examined using an electron backscatter image. See how ooid 10's cortex has been ravaged by dissolution. Some of the inner cortex tangential aragonite layers have been selectively removed. While ooid 10 was still in the marine realm, its cortex was extensively bored. These borings were filled with aragonite that shows minor dissolution. The outer 50 microns of the cortex has lost most of its layered aragonite, but retains its widely placed aragonite-filled borings. This outer cortex pore is now connected to the intergranular pores and probably underwent 2 periods of dissolution. The exposed base of the intergranular calcite cement crystals in the outer pore nucleated a second episode of calcite cement growth. These intracortex and intergranular calcite crystals have irregular, sinuous surfaces due to late-stage dissolution. The inner cortex in the box is magnified on the next slide. The aragonite lamina, about 2 microns wide, that have not completely dissolved, have irregular margins separated by slightly wider pores. The oval endolithic borings, some about 5 and some about 15 microns across, show less signs of dissolution. The larger borings on the left are filled with randomly oriented lath-shaped aragonite crystals that can be matched with images of modern ooids from the Schooner Keys, shown in my first video. The second Coral Gables waterway thin section is of a skeletal ooid grainstone that contains, in addition to ooids, halimeda fragments, gastropods, bivalves, and the decapod pellet Favrina. The intergranular pores are patchily filled with calcite cement. The ooids show a similar range of preservation types as noted for the first Miami section. Here, ooid 11 on the lower right, encased by intergranular cement and its cortex completely transformed to calcite, is singled out for discussion. Images of ooids, like this one of ooid 11, has been used to illustrate the process of calcitization, where a film of fluid about a micron wide sweeps across the cortex, dissolving aragonite on one side and simultaneously precipitating calcite on the other. The boxed area on the lower left is used to show as a step-by-step development of how ooid 11 became a ghostly apparition of its former self due to calcitization. ooid 11 grew its layered aragonite cortex while suspended during its transportation in seawater. Raised above sea level, its pores first became flooded with undersaturated rainwater. That then became supersaturated with respect to calcite, causing randomly oriented calcite crystals to be nucleated on ooid 11's surface at the red spots. Calcite grew from each nucleus, across the ooid's surface, and out into the intergranular pore. The crystal's growth surfaces are shown as simple rhombs. Crystallization continues, and where adjacent crystals meet, compromised intercrystalline boundaries form. Cementation of the intergranular pore around ooid 11 is now complete. A different type of calcite now invades the cortex aragonite. It is pictured here, starting from one or more points on the base of each intergranular calcite crystal, but is just as likely to start along their whole surfaces. The intergranular cement's crystallographic orientation is somehow transferred across the calcitization film to the new calcite, indicating the base of the intergranular crystals were present as calcitization took place. The irregular shape of the thin film shown here is a guess. Not all the aragonite is dissolved by movement of the thin film. Some is bypassed and preserves a ghost of its original cortex. As transformation proceeds, adjacent crystals meet along intercrystalline boundaries. Their positions at times follow the cortex's original laminated structure, and at other times cross-cuts the lamina. Transformation of ooid 11's cortex is now complete. The crosspolars image of the boxed area shows the extraordinary nature of the crystals that cross ooid 11's margin. One of these crystals, with pink birefringence outlined in red, is made of two parts, 1A and 1B, that grew at different times and in opposite directions. Calcitization is not the only process proposed that would account for ooid 11's transformation. Sala in 1992 proposed the aragonite could be partially dissolved. The pore created was then either left as a fluid-filled space or, as with ooid 11, was later cemented by calcite. With partial dissolution, there is no link between dissolution and cementation. In contrast, calcitization, they are coeval. With calcitization, inclusions that ghost the cortex's original structure pass across the calcitization front without moving more than the width of the front, a micron or less, so preserving the cortex's original structure. After selective dissolution, the inclusions that are left must be self-supporting, as they are surrounded by pore space. But do they move? Assessing inclusion support on a two-dimensional thin section image is difficult. So the last sample included here is of an ooid that underwent selective dissolution, but unlike ooid 11, was not subsequently cemented. So its inclusions must be self-supporting, however improbable this appears to be. The last sample is from a borehole core taken through Big Pine Key. Coniglio and Harrison, 1983. This sample has many different features, but only ooid 12 is discussed here. Ooid 12 was surrounded by coarsely crystalline calcite cement that, as with other ooids shown here from the Caribbean, preserve its shape while its cortex was largely dissolved. The diaphanous distribution of inclusions that ghost the ooid's original laminated cortex structure must be self-supporting, as they are surrounded by epoxy that fill pore space. Calcitization of aragonite has been performed experimentally and produces calcite that is texturally similar to that seen in ooid 11. However, this only occurs above 174 degrees Celsius. Casella and others, 2017. If this applies to the samples discussed in this video, their cortices cannot have been transformed by calcitization, as none have exceeded such a temperature. Sample limitations. The 7 samples used in this video are millimeter-sized pinpricks in the expanse of the freshwater systems in which they occur. Consequently, they show nothing of the spatial variations known to exist across these systems. The vadose thin sections used here are from the center of the vadose zone. They do not sample its top or base, where differing amounts of digenetic products are likely to be found, as shown for the Pacific Atoll Eniwetak by Sala in 2025. However, the 7 vadose samples demonstrate an increasing complexity with age, as each fluid incursion wreaked havoc on what was left by the previous incursion. And some of the petrographic relationships shown by these samples are at odds with widely accepted interpretations applied to these rocks. Crystal shape. Cement crystals in vadose sediments with concave final surfaces are frequently assigned to meniscus cement. Dunham in 1971 suggested, as a glowing crystal approaches a meniscus surface, the supply of ions to its growing point is reduced, manipulating its growth to replicate the meniscus surface. This works well for a single crystal, but when several crystals are involved, the situation changes. Each crystal is likely to arrive at the air-water interface at a different time, as the distance between their nucleation points and the meniscus surface, and the orientation of their fastest growth directions, vary. The first crystal to reach the meniscus surface will cause it to adjust its position. To cast a single curved concave surface from several calcite crystals seems unlikely. For this to happen, the meniscus surface must remain stationary, despite each crystal arriving there at a different time. The assignment of concave intergranular crystals to meniscus cement has been made for the Jultus vadose sample. However, it also contains convex surfaces that have either been missed or ignored. Convex surfaces do form on cement growing up to the air-water interface in speleothems, but in the Jultus sample, crystals with convex surfaces grew in random directions, ruling out such an origin. An explanation that would explain both concave and convex surfaces is that they are dissolution surfaces. The cross-polar images show how several differently oriented crystals are bound by smooth, concave, or convex surfaces. Intergranular pores in sediments in the vadose zone will be partly saturated for most of the time, and their air-water interfaces are meniscus surfaces. Interestingly, intergranular cement with concave surfaces are documented here from the Caribbean samples, but they are not present in the Mediterranean samples. The final surfaces on intergranular cement crystals formed by growth can be distinguished from those formed by dissolution if their internal growth surfaces can be revealed. Crystals growing up to an air-water interface will have internal surfaces that are concordant with the interface, while crystals that are dissolved will have internal growth surfaces that cut across the crystal's final surface. Unfortunately, the CL images of most intergranular cement crystals examined here reveal no internal growth surfaces. Early reaction sites. A sediment composed only of ooids has two pore systems with strikingly different transmissivities. A millimeter-sized, well-connected intergranular system and a nanometer-sized, poorly connected intragranular system. The intergranular pores are filled with fluid, the intragranular pores with mucilage. Shearman and others, 1970. Folk and Lynch, 2001. When undersaturated rainwater first enters the intergranular pores, it races past the ooids without dissolving them. Only when it becomes supersaturated does it leave a record of its presence, as cement in the intergranular pores. The source of carbonate for this cement was undoubtedly by dissolving aragonite, but where this happened and by what route it was transported in remains to be discovered. The intergranular fluid in the Mediterranean sites nucleated calcite more densely on its ooids than occurred in the Caribbean, perhaps due to its fluid achieving a higher supersaturation or magnesium content. Also, the Mediterranean crystals precipitated as a fringe on all ooid surfaces and kept their final growth surfaces, while the Caribbean crystals precipitated in clusters and their final growth surfaces were modified by dissolution. To speculate, these differences may be due to the Mediterranean climate being more amicable without the extreme fluctuations caused by hurricanes. While this was going on in the intergranular pores, organic-rich layers in ooid cortices were undergoing bacterial reactions, creating alkalinity that slowly dissolved adjacent aragonite. As the reactions in the two sites occurred independently, their relative timing is uncertain. Ooid cortices may have begun to react while still in the marine realm. Separation of the two sites ended when cortex aragonite next to the ooid rims was dissolved, allowing the encrusting intergranular cement to leak fluid into the cortex pores, causing calcite to grow there for the first time. Late reactions. The alteration of samples, while penetrated by fresh water for a few thousand years, is widely distributed. But after this initial alteration, digenetic events are spread irregularly, each event creating an ever-increasingly irregularly connected pore network. Aragonite that survives the early reactions can become isolated, so even after hundreds of thousands of years, it survives in some ooids, while adjacent ooids have become oomolds. Some final thoughts. Most petrographic interpretation of vadose rocks have been hung on hydrological models such as this one, which shows fixed hydraulic boundaries. This applies to fair weather conditions, where the pores in vadose sediments are filled mainly with air. Fluctuations in recharge are small. Fluid movement is slow, and equilibrium between water and rock can be achieved, so reactions slow or even stop. Rarely considered are the storms and hurricanes that affect all the sites considered here. Although short-lived, their fluctuations in recharge are extreme. The water table can climb above the land's surface. Undersaturated water floods vadose pore space, causing rapid reactions. The storm surge associated with Hurricane Irma submerged the surface of the supratidal flat on Little Ambergris Key beneath 2 meters of water in 2017. Jamieson, Todd and others, 2020. The 1,000-year-old Jutas Keys, according to Harris and others in 2024, were fashioned by 3 hurricanes over a period of 1,000 years. While storms and hurricanes may be short-lived, their cumulative effect on ooids that have existed for hundreds of thousands of years in the vadose zone may be more important in controlling their alteration than the longer times they spent under fair weather conditions. The petrographic relationships described here have been interpreted in a way that seems sensible to me. However, most petrographic relationships are ambiguous, and their interpretations need to be substantiated by independent data. This task is often accomplished by isotope studies. Analytical techniques for isotope analysis are constantly improving, requiring smaller and smaller samples. Isotope data has been collected for coarsely crystalline cement from vadose samples. However, their detailed petrography shown here includes several types whose precipitation was kinetically different and are separated by thousands of years. The first step in studying these rocks should be a thorough investigation of their petrography.